Imagine trying to run like a modern, futuristic metropolis. Soaring skyscrapers, high-speed rail networks, millions of blazing neon lights.
Sounds pretty energy intensive.
Right. But imagine you're trying to power that entire city using nothing but standard AA batteries. You would literally be spending every waking moment just, well, swapping out dead batteries.
Oh, the sheer volume of waste alone would be insane, not to mention the heat.
Exactly. The immense heat generated by the friction of all those tiny connections, the physical impossibility of coordinating it, it's just completely unsustainable. But the crazy thing is, when you look at the infrastructure powering today's artificial intelligence, we are essentially trying to run that exact same futuristic city on AA batteries.
Yeah, we really are.
Welcome to today's deep dive. We have a massive stack of sources in front of us today, ranging from some really dense technical substacks and forward-looking 2026 analyst reports to corporate PR releases and a heavily detailed 2023 annual report.
It's a lot of reading.
It is a ton of reading, and our mission today for you, the listener, is to synthesize this incredibly heavy material to uncover the hidden physical hardware bottlenecks that are quietly dictating the future of the AI revolution.
Because, everyone is hyper-focused on AI software, right? The language models, the coding.
Right, the software gets all the glory, but AI is ultimately a massive physical beast. And right now, that beast is slamming into a literal wall of heat and copper.
We tend to think of AI as this ethereal thing, just living up in the cloud. But the cloud is just a massive windowless building full of computers.
Yeah, very hot computers.
Exactly. And those computers are currently facing a brutal physical reality. If we look at the timeline mapped out in these reports, we are entering what analysts are calling phase 0 of the AI power grid.
Phase 0.
Yeah, phase 0. We're talking about the fundamental physical shift from moving data with electricity to moving it with light. And sitting right at the center of this massive transition is a tiny, incredibly under-the-radar Swedish company that has quietly positioned itself at the ultimate choke point of this entire global ecosystem.
But before we can even touch the futuristic optics or, the light speed data transfers, we have to deal with the immediate physical threat facing these data centers, which is basically keeping them from literally melting into a puddle of slag.
The heat problem is very real.
Oh, it's terrifying. Just looking at NVIDIA's current generation Blackwell B300 chip, the power draw is staggering. We're talking 1,400 watts for a single chip.
Which is just a massive amount of power for one component.
And it gets worse. Looking ahead to the 2026 and 2027 roadmaps in these reports, the upcoming Vera Rubin Kyber rack is projected to pull an astronomical 600 kilowatts per single server rack.
Right. And to put that 600 kilowatts into perspective for you, a standard legacy data center rack usually runs on a 54-volt architecture. And that 54-volt standard, well, it was originally designed for old-school servers drawing maybe 100 watts of power total.
Wow, so 100 watts versus 600,000 watts.
Exactly. We are talking about a mathematical leap that just completely breaks the existing infrastructure. Engineers refer to this crisis point as the 1,400 amp wall.
The 1,400 amp wall. Okay, unpack that for us.
So when you attempt to push 1,400 watts of power into a modern GPU die that operates at less than 1 volt, the physics become downright terrifying. You are funneling roughly 1,500 amps of electrical current into a piece of silicon the size of your thumbnail.
Which is insane because 1,500 amps, I read that's the amount of raw current required to start about 30 heavy-duty semi-trucks simultaneously.
Yeah, 30 semi-trucks.
And you are blasting that force into a single microchip. But looking at this purely from a layman's perspective, if the current is that massive, why not just use thicker copper cables to handle the flow? Just make the pokes bigger to handle the water pressure.
Well, that is the intuitive engineering solution, right? But it crashes headfirst into what the sources call the copper absurdity.
The copper absurdity. I like that.
If you try to run a massive 1 megawatt AI rack at the legacy 54 volts, the current is so intensely high that the resistive friction of those electrons moving through the copper would generate enough heat to literally melt the circuit boards.
Just melt them right down.
Right. So to prevent that heat buildup at 54 volts, you would need copper bus bars so incredibly thick that they would weigh nearly 200 kilograms per rack.
200 kilograms?
Yes. You physically would not have room to install the actual GPUs anymore. The rack would just be a solid 200-pound block of copper.
Wow. So we've literally run out of physical space. We can't use thicker wires because they just won't fit inside the building?
Exactly. which creates an absolute physics mandate for the entire industry. They have no choice but to transition the entire data center to an 800-volt DC architecture.
Okay, so bumping up the voltage.
Right. By pumping the voltage up to 800 volts, you can deliver that exact same massive amount of total power, but you do it with a tiny, highly pressurized trickle of current. Dropping the current reduces the copper requirements by roughly 50%.
Oh, wow.
Yeah, which gives you your rack space back and, more importantly, keeps the system from incinerating itself.
But pushing the entire grid to 800 volts introduces a completely new failure point, doesn't it? Because traditional silicon chips, the foundation of literally all modern electronics, they can't handle 800 volts of pressure. The reports note they physically break down and short circuit at around 600 volts.
They do. And that catastrophic failure point is what triggered the current material war happening inside the data center power grid. To handle 800 volts, the industry is moving away from basic silicon and entering the era of wide bandgap semiconductors.
Wide band gap. Okay, let's explain that simply for the listener.
So the band gap is essentially the invisible hurdle an electron has to jump over to conduct electricity through a material. Basic silicon has a very narrow band gap, about 1.1 electron volts.
So it's a very low hurdle.
Exactly. It's a low hurdle. Hit silicon with 800 volts and the electrons get overexcited. They easily jump that low hurdle when they aren't supposed to. The power leaks everywhere and the chip fries.
Which means we need materials with a much higher hurdle. And the two materials dominating these reports are gallium nitride, which we call GaN, and silicon carbide, known as Signicon. Both of these have a wide band gap of roughly 3.2 electron volts.
Right, the hurdle is nearly 3 times higher. They can block massive punishing voltages without leaking a single electron.
That's incredible.
It is. But GaN and SiGe are not just interchangeable replacements for silicon, They're actively carving out two very specific separate territories in the data center based on their physical properties.
Okay, so who goes where?
Well, silicon carbide is the rugged heavyweight of the two. It dominates at the facility perimeter, what the industry designates as layer P0 and P1. This is where the raw, massive power from the city grid first enters the building.
Oh, I see. And silicon is heavily utilized in EV chargers and low Earth orbit satellites too, right? Because its atomic bonds are incredibly strong. It's naturally radiation hardened.
Exactly. So if silicon carbide is this heavy-duty diesel engine handling the massive dirty grid voltage out at the perimeter, then gallium nitride GaN is the highly tuned, high-revving sports car engine.
A sports car engine. I love that analogy.
It really captures the dynamic perfectly. GaN is the absolute speed king of the materials. It wins at the rack-level step-downs, layers P2 and P3. That's where that 800-volt power gets quickly stepped down right before it hits the delicate GPU.
Okay, so right at the finish line.
Exactly. GaN has the unique ability to switch its power state on and off at frequencies approaching 1 megahertz. And because it switches so incredibly fast, the physical components surrounding the chip, like the magnetic inductors and capacitors, they don't need to hold on to energy for very long.
Which means they can be shrunk down.
Drastically. It allows engineers to build incredibly dense, tiny power modules that fit mere millimeters away from the GPU.
The technical substacks point out a really fascinating subplot here, though. There is a secondary war happening within the material war itself. It's not just GaN versus SynArc, it's about the physical architectural shape of the silicon carbide chips themselves. The trench versus planar battle.
Yeah, this comes down to microscopic real estate and electrical resistance. Legacy silicon carbide chips utilized a planar design. In a cleaner chip, the electrical current has to travel laterally across the flat surface of the chip before it can drop down and flow through.
So it's taking a massive horizontal detour.
Right. And that detour creates electrical resistance. And in physics, resistance always equals heat. Wolfspeed, one of the early major players in the space, heavily struggled with manufacturing yields because they stuck with these legacy planar designs while trying to scale up.
The heat profiles were just too difficult to manage.
Exactly. Meanwhile, companies like Infineon and RHM completely abandoned the flat surface and moved to a trench architecture.
Which means what exactly?
They're using specialized lasers to etch microscopic vertical U-shaped canyons or trenches directly into the silicon carbide.
Okay, so by etching those vertical trenches, the current no longer takes the horizontal detour. It just flows straight down the vertical walls of the canyon.
Right. You eliminate the surface friction, which allows you to pack the electrical switches much closer together. That single architectural change drops the electrical resistance of the chip by 30 to 50%.
Wow.
And lower resistance means significantly less heat, which is, the sole objective when you are trying to stabilize a 600 kilowatt AI rack.
Absolutely. So the wide bandgap materials, the heavy-duty SICKY diesel engines at the perimeter and the high-revving gallon sports cars at the rack, they successfully stopped the massive 800-volt power grid from melting the servers. But power delivery is really only half the equation here,
Just half.
because you still have to push terabytes of actual data between these massive 600-kilowatt racks. And if you try to push that volume of data through traditional copper Ethernet cables, the sheer friction of those data-carrying electrons generates its own massive heat wave.
Yeah, you would completely undo all the cooling and power efficiency you just saved.
Right, which forces the second massive physical transition we need to talk about. The data center must abandon electrons entirely and switch to photons. This is the photonics supercycle.
The photonic supercycle. To keep up with the data speeds demanded by generative AI, the industry is transitioning to co-packaged optics, or CPO. The conceptual framework our sources use for this is the glass city.
The glass city, that sounds so sci-fi.
It really does. We are basically replacing all the traditional copper data connections with microscopic optical circuits that transmit pulses of laser light.
So it's essentially traditional fiber optic internet, but shrunk down to a microscopic scale and baked directly onto the computer chips themselves.
Exactly. And the physical benefits of making that switch are staggering. Transitioning from copper to optical communication increases data processing speeds manifold, while simultaneously slashing the energy consumption of data transfer by up to 90%.
90%, that's huge.
It's game-changing. But to run a glass city, you need an extraordinarily reliable source of light. You need highly specialized light bulbs, specifically known as continuous wave or CW lasers. They act as the permanent power source for all these microscopic optical links.
Okay, let's unpack this. If the entire multi-trillion-dollar tech industry knows that we desperately need these specialized continuous wave lasers to build the glass city, who is actually manufacturing the light bulbs? I mean, if NVIDIA is buying up everything in sight, how is the rest of the industry getting their lasers?
Well, the short answer is they aren't.
Yeah.
Yeah, and that raises a terrifying supply chain bottleneck for the entire sector. Traditional optics manufacturing giants like Lumentum are completely saturated.
They're tapped out.
Completely. Their manufacturing capacity has been entirely consumed by massive, multi-year legacy orders from behemoths like NVIDIA. So they are physically tapped out. And that saturation has created a severe supply vacuum for every other hyperscaler trying to build out their own AI infrastructure.
Which brings us to the absolute core discovery of this entire deep dive. Sifting through these 2026 reports, there's a company that has quietly built a fortress right inside that supply vacuum. Sivers Semiconductors, ticker symbol SIVE.
Sivers.
Yeah, they are a tiny Swedish company with a manufacturing plant in Scotland. They only have 123 employees.
Which is tiny for this industry.
Very small. But 28 of those employees hold highly specialized PhDs.
They are heavily specialized. The analyst reports describe Sivers as the LED jet engine designers of the photonics supercycle.
LED jet engine designers, wow.
Yeah, they design highly efficient DFB or distributed feedback lasers, and they build them entirely on their proprietary NP100 platform.
Okay, and what is that exactly?
It utilizes indium phosphide instead of standard silicon.
Which makes perfect sense when you look at the physics of silicon, because silicon is what engineers call an indirect bandgap material. When you pump electricity into silicon, it's actually terrible at emitting light. It mostly just gets hot.
Exactly. But indium phosphide is a direct bandgap material. It easily converts electrical current into brilliant, pure light. And the distributed feedback aspect, the DFB part, is crucial.
How so?
Well, unlike a cheap laser pointer that scatters a messy range of wavelengths, a DFB laser has a microscopic corrugated grating built directly into the structure. It acts like a strict bouncer at a nightclub, only letting one highly specific, incredibly pure wavelength of light pass through.
Well, that's a great analogy, the bouncer.
Right, because when you are trying to pack dozens of different data streams into a single microscopic glass fiber, that purity is non-negotiable.
Right. The engineering is brilliant, but honestly, their engineering isn't what makes them the choke point. It's their manufacturing strategy. While giants like Lumentum got bogged down by the physical limits of their own internal factories, Sivers operates on a hybrid fabless model.
The hybrid fabless model.
Yeah. Years ago, they proactively locked in massive, dedicated manufacturer capacity with mass volume production foundries, specifically Win Semi. By securing that external factory space early, Sivers completely dodged the supply crunch that is currently suffocating their competitors.
So they didn't just design the best continuous wave light bulb, they made sure they were the only ones who actually had the factory floor space to print millions of them.
Exactly. It is the ultimate pick-and-shovel play in an AI gold rush. They aren't burning billions trying to build the AI themselves. They are just selling the highly specialized shovels that the hyperscalers desperately need to keep digging.
And we are already seeing the physical rollout of this strategy. Look at their collaboration with Jabil.
Oh yeah, Jabil.
Jabil is one of the largest and most influential optical manufacturers globally. Sivers partnered directly with them to engineer a 1.6T pluggable optical transceiver module.
Which means it can push 1.6 terabits of data per second?
Right. But the critical metric of that partnership is that the Sivers-powered module utilizes 2.5 times less energy than the standard alternative.
2.5 times less.
Yeah, in an industry currently dying of heat exhaustion, cutting energy use by that much is a massive paradigm shift. Jabil's own management publicly stated that integrating Sivers technology created a, quote, relatively dramatic moat for their product line.
So how deep does this Sivers moat actually go across the industry? Because when we map out who relies on these specific shovels, the web of hyperscaler connections is vast.
Oh, it's everywhere.
Sivers is listed as the default reference laser for global foundries. And just to be clear on what a reference laser means in hardware, Global Foundries literally prints the exact physical specifications and power requirements of the Sivers laser right into the base silicon blueprints they provide to their clients.
Which means if a client wants to use a different laser, they have to rip up the blueprint and re-engineer the entire board.
Exactly. That reference design maps Sivers directly to AI hardware heavyweights like Marvell Celestial, Lightmatter, and AMD's MI500 CPO program.
The integrations run deep. But perhaps the most direct volume indicator is their relationship with Ayar Labs.
Ayar Labs, yeah, they are a massive player in the optical space.
Huge. They recently raised $215 million and hold strategic partnerships with both Intel and NVIDIA. And Sivers is the only public laser supplier for Ayar Labs.
Wow, the only public one.
Yep. Recently, Sivers received an $11 million order from Ayar specifically to qualify high-volume production for generative AI applications. Sivers is no longer just a prototype partner, they are the volume engine.
And then there is the mystery customer. Digging into Sivers' 2023 annual report, they explicitly mentioned a Fortune 100 customer that submitted a request for, quote, an RFQ for 50 million laser units.
50 million units is a very specific number.
Right. Analysts heavily speculate that this mystery client is Apple, because the volume of 50 million units perfectly aligns with the annual production volume of the Apple Watch, a device that relies fundamentally on advanced optical sensing and consumer biometrics.
That makes a lot of sense.
Yeah, and if Sivers is designed into that hardware loop, this single contract could represent anywhere from 300 million to 2 billion Swedish krona in recurring annual revenue.
Taking a step back and looking at the broader financial projections mapped out in these sources, we are reviewing a report from a market analyst going by the name Serenity.
Okay.
This report projects that the co-packaged optics market will explode from nearly zero today to between $81 billion and $91 billion over the next year and a half. The analyst even speculates that Sivers could replicate the historical growth path of Lumentum, potentially reaching a $75 billion market cap.
Okay, we have to pause and be incredibly clear right here for everyone listening. We are impartially reviewing the contents of these 2026 analyst reports just to map out the broader industry expectations. We are not endorsing these massive financial projections, right?
Absolutely not.
And we are absolutely not taking sides on any third-party stock speculation. We're just conveying the information. But I mean, even if you completely discount the financial hype, the underlying engineering reality of why the market is making these bets is undeniable. It all comes down to the mechanism of design in lock-in.
Right, because hardware infrastructure operates under completely different rules than software. You cannot simply push an over-the-air update and magically swap out your laser supplier.
It's physical.
Very physical. Sivers indium phosphide lasers are deeply physically integrated into the optical circuitry of multi-billion-dollar rack architectures. Once a hyperscaler commits to a specific Sivers laser, they have to physically calibrate their liquid cooling loops to manage its exact heat output.
Oh, well.
Yeah, and they have to hard code their firmware to match its exact microscopic timing. Once that multi-billion-dollar data center is built, they are fundamentally married to that specific laser supplier for years. You cannot swap it out without ripping up the floorboards and re-engineering the entire facility.
It is the ultimate sticky product. So what does this all mean for you, the listener? Today, we have traced the invisible physical architecture of the entire AI revolution.
We covered a lot of ground.
We did. We started at the brutal 800-volt power survival mandate. We waded through the heavy-duty sick diesel engines and high-revving GAN sports cars of the material wars. We traveled down the photonic light highways of the glass city to avoid the friction of copper. And finally, we landed on a microscopic 123-person Swedish company holding the critical light bulb choke point for the entire global ecosystem.
The overriding takeaway from this stack of sources is that true technological revolutions are never just software updates. The limitless potential of software is always deeply, violently constrained by the limits of extreme physical engineering.
Software scales infinitely in theory, but hardware melts in reality.
Exactly. Knowing these specific hardware bottlenecks, really understanding the 1400 amp wall and the photonic supply vacuum, gives you a completely new X-ray lens for reading future tech headlines.
So true. The next time you see a massive tech giant announce a new, world-changing AI model, you will know to look past the software and ask the physical questions.
Yeah.
How are they stepping down the voltage, and who is printing their lasers?
It completely changes how you view the infrastructure around us.
It really does, and it leaves us with one final, provocative thought to mull over. If we are currently being forced to shift the entire foundation of human computing from electrons to photons just to keep up with today's generative AI models, what fundamental physical laws will we have to break when quantum computing and artificial intelligence fully merge in the next decade?
That's a terrifying thought.
Right. If we are already abandoning copper because electrons generate too much friction, will the speed of light itself eventually become our next insurmountable bottleneck? When that happens, we might just find ourselves standing in the middle of our futuristic metropolis, realizing that once again, our incredible new city is being run on the equivalent of AA batteries.
A truly fascinating physical problem for the engineers of the 2030s to solve.
Absolutely. Until next time, keep diving deep.